Hey everyone, I'm Matt Fleming. I'm super excited to be talking at P99. And this talk is going to be all about using change point detection to find noisy benchmark results. Anybody that's done benchmarking knows that it's difficult to figure out if your software is losing performance over time or even gaining performance. So hopefully in the next 15 or 20 minutes, I can convince you that change point detection could be a really good tool to add to your toolbox. A little bit about me. I used to be a Linux kernel maintainer, but for the last decade or so, I've really been focused on performance of distributed systems, operating systems, and databases. I've co-authored a couple of papers in this field on change point detection and on distributed systems. And I like running. I like running benchmarks. I like running on the treadmill. Before we go any further, we really need to get on the same page when we're talking about noise. Noise can mean lots of things to lots of different people, so it's good to have a succinct understanding of that. So when I say noise, what I mean is something that has high variability. If you run a benchmark multiple times without changing anything to do with the system, the software, or the infrastructure, does the range of values you get back from the benchmark adhere to like a small number of values, or is it spread over a large range? If there's a lot of values, then that's noisy. Those are noisy benchmark results. This can be really problematic for later stages of analysis with benchmarks because it's difficult to figure out if you have a wide spread of results, whether the software change you introduced actually affected performance. The crucial thing about noise and benchmarks is things are noisy if you don't change the parts of the system you care about. There's always randomness and events going on, but the crucial part is, are there changes to the system that you're testing? And that can be at various levels of the software stack or even the hardware stack. So visually, when I say noise, this is what I mean. This spike here on the left of the chart, this is noise. And what this represents is a essentially random value. Now, it's difficult for you as the observer to know that this is noise because you need to know a little bit more about the data and the benchmark that was run. But I know that there was no changes to the parts of the stack that I care about for these few weeks where I measured this. When I reran the benchmark and measured the results. So this spike is an outlier. There was no fundamental change to the software. And like I said, this can make it really difficult for further steps in analysis and figuring out, like, if you were to make changes, can you attribute that to your software changes, or is it just randomness and noise? Now, noise comes from the indeterminism in modern systems. We build systems this way, and a lot of the times that's really useful. Anytime you have a shared resource that can be contended, potentially that could introduce some noise. If you know Little's law, as you push the utilization of anything towards 100%, you get queuing, and this is a non-deterministic step in your software, and that can also introduce noise. Crucially, all modern systems have some amount of noise. You can reduce it, but I don't think you can ever fully eliminate it. And it's important it's important to understand the trade-off for eliminating noise is that it's a trade-off. You can invest time and energy, but at some point it becomes not worth the effort. So we have to have methods and techniques for dealing with noise in our benchmark results. So here's an example of a source of noise. This is probably the most common example that I've personally run into. This chart shows the CPU frequency on a public GitHub runner as a benchmark was running. So the CPU frequency can be scaled in modern systems to trade off power and performance. If you scale the frequency up, you get increased power, increased clock speed, but it uses more power, and you get better performance. On the other hand, if you scale it down, you save power, but you lose some performance. And this chart shows that the Linux host that was running this benchmark is basically scaling the frequency up and down in response to demand from the benchmark. Now, that's maybe great for saving power and making this trade-off between power and performance, but it's not great for reliable benchmark results because this will affect from run to run the actual values you get from the benchmarks. So I'm not suggesting anyone's doing this, but if you are looking at using a public GitHub run to run benchmarks, hopefully this slide will convince you not to do that. Here's another illustration of a source of noise. This is Apache Cassandra, which is an open source distributed database. And the graph shows the receive throughput as a client is sending what is supposed to be a constant load to the server. But you can see from the chart that it's not really constant. Like the graph is going up and down. We have some peaks and valleys. And the valleys tend to coincide with when the Java garbage collector ran. Apache Cassandra is written in Java. So this is an example of how your runtime and your tools and languages can also be a source of noise. So the takeaway from the first section is all systems contain noise. You can reduce it, but probably never fully eliminate it. And exactly how much you want to reduce is a trade-off because it costs time and energy to remove it. So if we're going to have to deal with noise, we have to live with it, we need some methods and tools for kind of combating that. If you imagine like a sophistication ladder for combating noise, maybe the bottom rung on the ladder would be you can take your time series data or your benchmark data, put it in a graph, and just stare at it. And I would argue that most of the time you need to do some visual analysis. The human brain is amazing for finding patterns in things. And it's always a good step in any analysis to just stare at the charts. But I would say that it shouldn't be the first step. So when I talk about eyeballing charts, I don't think it's a good idea to do this first in any analysis step, and definitely not to only do this step. But if you have nothing, if you're not looking at charts today or results, maybe this is a good initial step into the looking at performance results. But eyeballing charts has downsides, which is that it's super laborious. It's time consuming. I know teams where an engineer on the team every morning will look at the charts from the results that came in overnight. And it's difficult to teach other people on the team or onboard new engineers and show them how to do this. What tends to happen is you have some engineers who either volunteer to do this, checking of the charts, or get picked to do it, and they just develop a better intuition. And there's a very real problem with institutional knowledge with this methodology, which is that a certain number of people, or usually, let's be honest, it's one person on the team, really knows how to analyze the charts and spot regressions or performance improvements, but it's hard to teach anybody else on the team that. So what else can you do? A slightly more sophisticated thing is to have thresholds. So when I say a threshold, what I mean is you as a team would decide that any benchmark result plus or minus, let's say 15%, would be considered a significant performance change. This is slightly better than eyeballing it because now you're automating the analysis step. You're taking the human factor out of it and using machines to do it in an unbiased way. But this can quickly balloon and get out of hand because it's rare that you will test a single benchmark or a single test. What usually happens is you want to maintain a threshold per line in your configuration matrix or your testing matrix. So if you have multiple architectures that you run your software on, that gets multiplied out. You maybe want a threshold per architecture because it's unlikely they would be exactly the same and exhibit exactly the same variation in the results. And then if you have different tests and product lines, you can begin to see how the threshold-based method kind of discourages you from adding new things, which is not what you want. You need an easy way to basically improve your testing, add new tests, and new product lines. So thresholds are better than just eyeballing it, but really they don't scale. So what else can we do? We can use change point detection. Change point detection is actually a really old mathematical technique. I think it originally comes from the signal processing community, but it's been used in a bunch of areas such as climate change, fraud detection, and biomedical research. And the literature for change point detection algorithms is vast. It's been around for decades. And it's only in the last, I would say, 5 or 6 years that we've started to see these tools, these different CPD algorithms used for performance analysis. I first became aware of this in about 2020 when MongoDB published this paper. And at the time when I read this just completely blew my mind. I thought this was amazing. I was working on the same problem, which was analyzing benchmark results and trying to figure out if new releases of the Linux kernel had any performance regressions. And this seemed like an amazing solution to that problem. So I reached out to the authors. I ended up founding a company, one of the co-authors, and also writing a subsequent paper on using change point detection. So though the literature is vast and wide, I'm going to try and condense it down into a single slide and give you a very high-level overview of how all the CPD algorithms work. Essentially, you have three phases of the algorithms, and exactly how they're implemented varies with the algorithm, but the search phase is responsible for finding chunks of the time series and then passing them to the comparison function. The comparison function will do the comparisons and decide on potential change points, which is points in the time series distribution where there was a shift. And finally, these get passed to a filter function. Now, the filter function is essentially working with the output of the first two steps to find statistically significant change points in the time series data. There is a few open source libraries that implement different change point algorithms. The signal processing library from MongoDB came along with the original paper in 2020, and it's got a Python wrapper around it. I think the library, the algorithm is written in C, wrapped in Python, so it's pretty performant implementation. Perfilizer, if you use .NET or C#, is used in benchmark.net. And this, again, has different CPD algorithms that are used for analyzing results. Ruptures is more of a general purpose change point detection Python library. It isn't specifically for benchmark results or benchmarking. And Hunter is some software that was written after co-authoring the paper that I mentioned, that I co-authored. That also is written in Python. So what can you do with this? Let's look at an example. So this is a time series collection of benchmark results for the Linux kernel for Linus's tree. So this is like the major releases from Linus's tree and the release candidates. Plotted as a time series, so going back historically. For the last, I think it was 150 results or so. So that goes back a few years. And you can see the red dots in the time series are when the Hunter library has detected statistically significant change points. If we focus on the change point on the far right, because this is a time series, and so things are chronologically ordered with the blue arrow, that change point highlights a kernel release where the duration of system calls increased. So there was a performance regression in Linux system calls. This benchmark measures the get parent PID system call. And when I dug into this, what I found was that it was a new Spectre mitigation introduced in April of this year and turned on by default for KVM guests. So Spectre has been pretty much a disaster from a performance perspective, though it's an important and necessary tool for security. It's been a disaster for system call overhead. And even now, many years later, after the original version, continues to wreak havoc on performance. So I obviously am not suggesting that CPD will solve all your problems. There is no silver bullet in any of this. The real world is messy. And CPD, like most other techniques, does have some drawbacks. For example, because of the way I explained how the algorithm works, you do need multiple data points before a change point can be identified. So this varies with the implementation and the algorithm. For Hunter, it's typically about 5 data points, and then you can find a statistically significant change in the time series. Also, what sometimes happens is there's a delay in surfacing a change point. If you imagine that you collect benchmark results every day, Monday to Friday, you may only discover on Friday a change point for a result you submit on Wednesday, because as the algorithm gets a more holistic view of the data, only then can it surface the change point. So there is something of a delay when you use change point algorithms. And finally, the way that most of the comparison functions work is, and in fact, one of the powers of CPD is that it does a pairwise comparison between all the data points. So this gives it the power of finding these shifts in the underlying distribution, but it is computationally quite expensive. because you have to do this pairwise comparison and vary the size of the clusters that you're comparing. ON squared is typically the fastest that I'm aware of, but these can go up to ON cubed and worse for some of the implementations of the algorithms. If you'd like to learn more about CPD, there's a couple of research papers that I've highlighted here. The ones at the top are survey papers, so they cover a wide range of different algorithms and with excellent references, and these provide a good introduction to the general mechanism of CPD algorithms and how they work. And the bottom two is the Mongo paper, and then the follow-up paper that I co-wrote on Hunter. And that's it. Thank you very much for your time. Please reach out, and you can contact me at these addresses. I'd love any feedback, and if you've got any questions. Thanks a lot.